Welcome to this lecture in the 0007 series. Today we're going to talk about insulin. So, if you haven't done so already, get yourself a hot drink. I've got mine here. Or, if you prefer, get yourself a cold drink. Either way, get yourself ready, sit down, relax, and let's make a start. Let's start by looking at the learning outcomes you should be able to achieve after these two lectures. And I should point out here, this is a two-part lecture. So this lecture is part one, and we're going to come back to some of these concepts next week in part two. So you should be able to define the blood glucose concentrations that are recommended to be maintained by diabetics. You should be able to describe the structure of insulins, that's its biological structure, and it's got a primary, secondary, tertiary and quaternary structure, so you should know that. And you should also know the difference between the wild type insulin, so the native human insulin, and its synthetic analogues, because there are quite a few. And in fact we are going to talk about those synthetic analogues today and then stop. Next week we're going to talk about routes of delivery. You should be able to discuss the routes of insulin delivery, not after today's lecture but after next week's, and how it's used in practice. And you should be able to explain the benefits and drawbacks of synthetic insulin analogues. So if someone comes into your pharmacy and they say, right, I've been talking to my doctor and he or she has said I need to look at this different type of insulin, why is it different? You should be able to explain to that patient what the different synthetic analogues of insulin do. Okay. So with that, let's make a start. I have to say right at the start, a lot of the information in this lecture is rather factual. And so I apologise for that. There's no escaping from it. There is just a lot of factual information. So what's going to appear on the screen, I'm going to talk through, but some of it you just have to remember. There's no escaping from it. Okay. Starting with the basics of what actually is insulin. I'm sure you know what insulin is. It's a hormone. It's secreted by the pancreas in response to rising blood glucose levels. Okay. Typically, levels of glucose are going to rise in the blood after you've eaten, and they're going to rise either faster or slower depending on what type of food you've eaten. If you've eaten something that's got lots of refined sugar, you're going to get quite a high sugar rush, aren't you? Whereas if you've eaten something that contains lots of complex carbohydrates, for instance, you'll probably get a more sustained glucose level, but it will be a lower peak. But in any event, the pancreas releases insulin to try and remove glucose from the bloodstream. I'm going to go into why you want to get glucose out of the blood in just a little bit. So it does two things, insulin. One, it instructs cells to absorb glucose, and two, it also instructs those cells to burn that glucose for energy. Okay, there are some cells that will store glucose for future use as a glycogen, and those are muscle cells and liver cells. But in the main, insulin is telling the cells, can you please take glucose from the blood and burn it for energy, because it's trying to get the glucose out of your blood. If you have some sort of disorder with insulin, then you have diabetes, and there are two types of diabetes. Type 1 is where the patient can't themselves synthesize insulin in the first place. So that's a sort of genetic condition that you're born with, and you really can't do anything about it. It has to be managed by giving insulin to the patient. But patients with type 2 diabetes, that's where the cells in the body have become resistant to the message that insulin is giving them. So you take in glucose, your blood glucose level rises, insulin is released by the pancreas and it's instructing the cells to take up that glucose, but the cells aren't listening. And so your body has to start secreting more and more insulin in order to get the glucose into the cells, and we get into this sort of runaway cycle where the cells are becoming more and more insulin resistant, and so your body is producing more and more insulin in response, and it's a big cycle. So patients with type 2 diabetes often develops in later life, and also it can be reversed or managed through diet as well, because that's how the patients got there in the first place. In both cases, however, if it's not treated, you've got circulating glucose in the blood at reasonably high levels, and that's really bad for reasons I'm going to come back to probably next week. What is structure of insulin? It is shown on the slide in front of you. Insulin is a dipeptide chain, so two peptide chains that are joined together. I'm going to look at that in just a second. Chain A has 21 amino acids, chain B has 30 amino acids. You might say to me, okay sir, do I need to remember the sequence of amino acids in these two chains for the exam? And the answer is, Clearly not. For two reasons. One, I'm never going to ask that question because it's not important. And two, it's an open book exam this year, isn't it? So you could just write it down because it'd be on the screen in front of you. So you do not need to know the actual sequences of amino acids. You just need to know it's two chains that are joined together. One has 21 amino acids and one has 30 amino acids. It is kind of important when we look at some of the other insulins. So that's insulin from either cows or pigs, or some of the synthetic insulins. Then they do change their amino acid sequence slightly, and it is kind of important that you recognise what the change is. So you don't need to know the whole amino acid sequence, but you do need to know which amino acid or acids have changed in the different synthetic analogues. But again, we'll come to that at the end of today's lecture. Okay, so for now, don't worry about it. So the primary structure is 2 amino acid chains, 21 amino acids and 30 amino acids in length. However, the insulin also has secondary, tertiary and quaternary structures. What would those be? I hear you ask, and the answer is shown on the screen in front of you. The secondary structure is those regions of the peptide chain that form either alpha helices or beta sheets. In insulin there are no beta sheets, but there are a number of alpha helices. There are 2 helices in chain A and there's 1 helix in chain B. The tertiary structure is related to how the chains come together, and if you noticed on the slide previously, there are 3 disulfide bonds holding the 2 chains together. Those are between A7 and B7, so that's the 7th amino acid in the A chain and the 7th amino acid in the B chain. A20 and B19, so 20th amino acid in the A chain, 19th in the B chain, and then chain A itself is folded over and there's 1 disulfide bond creating a loop in the A chain between residues 6 and 11. Insulin also has a quaternary structure, which is something you may not have heard of before. So again, there's an image of it on the screen. So the quaternary structure is not about the beta sheets and the alpha helix. It's about how the insulin molecules come together in solution. Okay, so insulin does not exist in solution by itself. What it does is, when you dissolve it, 2 insulin molecules will come together and they'll form a dimer. So if you do nothing else, insulin in solution forms a dimer with 2 insulin molecules bound together. But if you add zinc, so remember zinc is a metal, so if it has zinc ion, then large proteins can often coalesce around metal ions. So if you add zinc, then insulin forms a hexamer. Hexamer means 6 of. So 6 insulin molecules come together and they group around the zinc. Okay. The reason there are 6 is because actually the insulins themselves are in dimers, as they always are in solution, and then 3 of those dimers coalesce around zinc ion. And it's kind of important that you remember this, because when we look at some of the long-acting insulin formulations in a little bit, starting with something which is a hexamer is kind of important, because the insulin can't act in the body while it's bound up in this hexamer form, and so in order for it to act on cells, it's got to kind of dissociate itself from this hexamer, and so that slows it down. And so one way of generating a long-acting insulin is to add zinc to the formulation, because that causes this hexamer formation and that slows the rate of dissolution. Okay, so you might be thinking, why are we talking about all these different structures, sir? The answer is because it's kind of important when we look at how we might control the rate at which insulin is released in the body later on. Where do we get insulin from? Clearly, in some cases the patient is not producing insulin themselves, and in other cases they're not producing enough for the cells to respond. And we can do a number of things. What used to happen most is that insulin would be obtained from other animals, typically beef, cows and pigs, so porcine and bovine insulin. And these are referred to as natural insulins. Natural because they're naturally occurring and they haven't been synthetically made in a laboratory. They're usually obtained from the pancreas of the animals from abattoirs. It's kind of important that the animals themselves must be certified fit for human consumption, and they must be free from TSE disease. Now I know what you're thinking. I bet you want to say that, don't you, sir? Transmissible spongiform encephalopathies, but I find that really difficult to say. So TSE is a lot easier to say, so mad cow diseases and that sort of thing. The animals must be free from that. One of the things which is kind of important is that the US doesn't permit beef or porcine insulins because of the risk of TSC actually. The purification process itself is also quite long and complex. You've got to extract the insulin from the pancreatic cells, but obviously you're going to extract quite a lot of stuff at the same time, and you've got to go through a rather long process of purification and analysis to make sure that you've got the right molecule. There is little difference though between porcine and bovine insulins and human insulins, as shown in the table in front of you. I think you can see that bovine insulin has 3 changes from human insulin. So that's the threonine at A8 is changed for alanine, the isoleucine at A10 is changed for valine, and the threonine at B30 is changed for alanine. So 3 changes in the amino acid sequence for bovine. Porcine, on the other hand, there's only one difference, isn't there, which is at B30 where threonine is changed for alanine. So only one amino acid difference for porcine. So in order to make insulins from animal sources a little bit closer to human insulin, it is possible to chemically change them so that you get the amino acid sequences to be exactly the same. It's clearly easier to do this with porcine insulin than with bovine insulin because there's only one amino acid that needs to be changed, and it is done with an enzyme reaction to change the B30 residue from alanine back to threonine. So if that's done, so it's from a porcine source but it's been modified to make it the same as human insulin, it must be labelled EMP, which is enzyme modified porcine insulin. So if you see EMP on a label, that's what it means. Because of the worry about extracting insulins from animal sources, it's also possible to make human insulins from biosynthetic pathways. So you do that with recombinant DNA technology. So you take a bacterial species usually, or it can be a yeast as well. And so you insert a plasmid that enables the yeast or the bacterium to code the insulin, and so you ferment those bacteria or yeasts, and then you harvest the insulin. No different from how some of the vaccines for COVID are being made actually at the moment. If the insulin has been made this way, the label must state PRB or CRB, which stands for purified recombinant bacterial. At least that's what PRB stands for. I have no idea what CRB stands for. I did try and look it up, but I couldn't find it. It just says CRB. And PYR stands for purified yeast recombinant. So again, the label is telling you something about how the insulin you're dispensing was made. Okay. One other thing is that the strength of insulin in the dosage form is kind of important. We're going to look at that more next week when we look at insulin pens actually. But for now, it's simply to note that the concentration of insulin is defined in international units, or RU. 1 unit is equivalent to, for human insulin anyway, 0.0347 milligrams. And then the masses are slightly different for bovine and porcine, 342 and 345, because they contain different amino acid sequences, and so the molecular weights are slightly different. Okay. That becomes kind of important later on when you think about talking to a patient about their device, because the device can be set in terms of RU, and so you need to be able to convert from RU to milligrams to be able to work out some of the doses sometimes. Okay. Now, how is insulin delivered? If I asked you, is insulin available in tablets? I think you'd probably say to me, no sir, it's not available in tablets, it's injected. Everybody knows it's injected. Yeah. So the answer is, it's injected. Yeah, you knew that, didn't you? And the reason it's injected rather than given orally is because insulin is a protein, isn't it? And so the first thing that's going to happen is the insulin is going to touch your stomach acid, and like any other protein that you might ingest, the stomach acid is going to hydrolyse it, and so it won't get out the other side of the stomach, and there'll be no insulin to be absorbed. So it's given by injection. Usually it's subcutaneous injection because you don't want the insulin going directly into the bloodstream. You want it released over a period of time because you're trying to mimic the endogenous release profile of insulin from the pancreas. And the pancreas does not release an entire amount of insulin into the blood in one go. It releases it gradually. So you're trying to mimic what the pancreas would do naturally. Sometimes insulin is given intramuscularly and sometimes it's given intravenously, but really only in emergency situations where someone's in some sort of diabetic coma and you really need a response very quickly because there's too much, in that instance, too much glucose. If there's too little glucose on the other hand, then glucose has to be given intravenously. Where are the injection sites? They're typically thighs, upper arms, buttocks or abdominal wall, and the user needs to rotate the site of injection, and the reason is because if you don't do that, you're at risk of lipohypertrophy. And so what you sometimes see in patients who constantly inject in the same place is they get a build-up of fat as a ball underneath the surface of the skin. There's an example shown on the screen. And so that's a collection of fat which has accumulated around the multiple injection sites. So it's really important to say to a patient, you need to inject at multiple places to stop this happening. Absorption is usually fastest if you inject into the abdominal wall. And so sometimes if someone's forgotten to inject and they need a relatively rapid onset of insulin, it's better to advise them to inject into the abdominal wall. Now, there's a whole range of insulin injectable formulations, and you're going to come across some of these names. So it's kind of important to understand what the difference is between them, because at a first approximation you might think they're the same, but they are in fact not the same. And the reason is, as we'll see in a moment, we are trying to mimic the endogenous release rates of insulin from the pancreas, and so we don't necessarily want to just inject a completely water-soluble form of insulin because it will get into the bloodstream way too fast, and so we want to try and slow it down. So the options are soluble insulin or neutral insulin. It's just a solution of insulin in the dimer form. And if you think about that, that's going to be the fastest dissolving, isn't it? Because that's how insulin normally exists in solution, in the dimer form. So it's ready to go. There's nothing else it needs to do. The next one is insulin zinc suspension. So zinc, remember from before, is the ion that the insulin dimers can coalesce around, and it's going to form a hexamer. So that right there is a rate limiting step for dissolution, because the hexamer's got to come apart before it can dissolve. And it's also possible to make the hexamer as either a crystalline or an amorphous powder. I'm going to come back to what that means for dissolution rates on the next slide, so don't worry about it right now. But it's also important to note that you can get short-acting or long-acting zinc suspension insulins. Short-acting will be amorphous and long-acting are crystalline. It's also possible to mix those two in specific ratios to change the rate of onset. Isophane insulin, or neutral protamine hagedorn, that's difficult to say, isn't it, is an insulin complex with protamine. So again, it's the same deal, you're just slowing the rate of dissolution down. Protamine zinc insulin is insulin complex with both protamine and zinc, so it's the same as the two above, but now you've got a lot more bonding going on. And biphasic isophane insulin is a mixture of protamine insulin and soluble insulin. In all cases, you're simply trying to create a dissolution profile by mixing different types of insulin together. Why are there so many types of insulins? And I alluded to this already. It's because to act in the body, insulin really needs to be in the monomeric form really, but it's always going to be a dimer form in solution. And so in order to slow down the rate of dissolution, you kind of want to make it harder for it to dissolve. And it can be harder because you've complexed it with something, so the zinc or the protamine, or because you've changed its physical form. I'm sure you remember, because we talked about crystalline and amorphous materials in a separate lecture. Amorphous materials have no crystalline structure, and so less bonding holding all the molecules together, and therefore they dissolve faster than their crystalline counterparts. The other thing about crystalline particles is it's possible to control the particle size. So the larger the particle size, the lower the surface area, and so the slower the rate of dissolution. So you can change the rate of dissolution of the insulin by doing a number of things, making it amorphous or crystalline, complexed or not complexed, and then you can mix them all together. So it's possible to fine-tune the dissolution profile in many ways by mixing all these things together. What you are trying to do is create a pharmacokinetic profile that matches what might happen in the body. So on the screen in front of you are some typical profiles So insulin activity on the y-axis is a function of time following administration on the x-axis, and you can see that the table includes onset, peak and duration values for all of these different types. Soluble insulin is obviously going to be the fastest because the insulin doesn't have to do anything, it's already in solution. So it'll have an onset of roughly 30 minutes to an hour, peak of 2 to 4 hours and duration of about 8 hours. After that, I should say the fastest actually is soluble IV, but that's immediate because it's not doing anything. It's not coming out of the muscle, it's straight into the blood. So that's not something that would normally be given to a patient. So soluble subcutaneous insulin is going to be the fastest for a conventional patient. And then as you go down the table, you can see that as you do some of these other things, you make a crystalline zinc suspension, amorphous zinc suspension, a mixture of crystalline and amorphous, you can really fine tune the profiles. So pure crystalline, 4 to 6 hours onset, amorphous 1 to 2 because it's faster dissolving, a mixture of crystalline and amorphous 1 to 3. So you really start to fine tune these profiles depending on what the individual patient needs. It's one of the reasons why you really don't want to be giving a patient different types of insulin week on week. A patient needs to know which type of insulin is good for them, and then they need to use that consistently, because if they don't, they're going to get a different response after eating food, and patients don't want that. So it's really important to try and understand which one of these formulations they need and to make sure they take the same one every week. Okay, right, we're going to stop for a cup of tea. When we come back, we're going to look at some novel insulin analogues, and when we've done that, the lecture's over and we have to come back next week. So I'll see you in a bit.